So hello everyone again. This is lecture 6 part 1 of current electricity. Today we will go on with the further discussions of Kirchhoff's law. In the previous lecture we completed the cells in series and parallel. Today we will go on with the Kirchhoff's law. What are Kirchhoff's law? So basically there are two rules which are to be applied if there is a complex series of cells, resistors and so on. So how to apply those will be dealt in this concept in this lecture here, and then we will move on with the applications of Kirchhoff's law or application of current electricity as a own, for example potentiometer, meter bridge, etc. So let us not waste any time. I am Sameer Lavankar. Let us begin our discussion. Okay, so a course outline for you, first of all, to let you know what all things are being completed. So first of all we started with the introduction, in which we understood the concept that if the electric charges are moving, that constitutes an electric current. What is the difference between electric charges being at rest and electric charge being moving? Then we understood that there has to be, for the application or for using this electricity in our day to day appliances, we need to consume, or we need to make sure of that these are in steady phase, not in unsteady phase. If they are unsteady, such as lightning which comes from the clouds to the earth, it can't be used appropriately. So a steady current has to be needed for the more efficient use of this current electricity. In the second point of electric current, we understood the mathematical formulation of current, that is small q by t. That is, if I take a area A through which charges passes from the left side to right side, then if in time t the amount of charges which are passing is small q, then the current is nothing but small q by t. In infinitesimal method, we can denote this current as equal to limit delta t tending to 0 del q upon del t. In the third point, then electric current in conductors, we understood the concept of three materials such as conductors, semiconductors and insulators, in which the complete concept depends upon either the charges are free to move or they are fixed in nature. If they are more fixed, then it is constituting an insulator, and if they are free to move, then it is constituting an a conductor. Mid of that is semiconductors for you. Then in the Ohm's law, we understood the concept of V directly proportional to I. So V directly proportional to I, and if we remove the proportionality sign, we got that V is equal to IR, where I is nothing but resistance, which is denoted by capital R and has a unit of ohms. Then also we understood that resistance is directly proportional to L upon A. Therefore we got R is equal to rho L by A. Here rho is nothing but resistivity. Okay, so this thing has also been explained. In the fifth concept of drift of electrons and the origin of resistivity, I explained you the concept of small Vd, and finally using a different concept such as J, capital Vd, tau, etc., we found out the value of conductivity, which is equal to 1 by resistivity. Hence origin of resistivity was being explained. In the next concept of 6, that is limitations of Ohm law, we understood the concept of three different ways in which the Ohm's law, that is V is equal to IR, is not being proportionalized. That is, this graph is not a straight line, the slope is always not a straight line. We also understood that if the voltage potential difference is reversed in diode, then the graph is not the same in the downward direction in the third quadrant basically. And also we understood a material called as gallium arsenide, which also does not show the Ohm's law, which does not follow the Ohm's law. So these are the three limitations of Ohm's law. Then the resistivity of various materials, we understood about the color coding of carbon resistors, in which there were 4 colors, and the last color denotes the tolerance, and the first 3 colors denotes the multiplier as well as the two significant digits. Now in the temperature dependent resistivity, we understood the concept of as the temperature increases, thus the conductivity decreases or increases as far as the material is considered. So we understood in this concept that the conductor shows the opposite sign as that of semiconductor and insulator. So these are the first 8 points. Then the next point, we understood the concept of electrical energy and power, in which we understood the formula that power is nothing but product of V into I. Also using the Ohm's law, we understood two different formulas, that is power is equal to I square R and also equal to V square by R. Then the combination of resistors, we understood that R equivalent for series is nothing but the summation of all, that is R1 plus R2 plus R3 dot till Rn, and in parallel we understood 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 dot till 1 by Rn. Then the cell's EMF and internal resistance, we understood that every cell, even if a producing battery concept, everything which produces battery does not have a is not an ideal case, therefore there will be a resistance for that too, hence it will be internal resistance which is denoted by small r, hence the complete EMF will be added up of complete equivalent resistance which is external plus the equivalent resistance of internal also. So it will be some, if we are if it is in series, then it is capital R plus small r. Then cells in series and parallel, we understood the concept of epsilon equivalent for series and parallel. And finally, today we will go on with the Kirchhoff's rules. So let us move on with the Kirchhoff's rules only, and then we will move on with the final applications of Wheatstone bridge, meter bridge and potentiometer, and that will be the end of current electricity. Okay, so Kirchhoff's rules. So I think this has been explained in the previous lecture only. So let us move on with the rules only, that what are the rules and proofs. So first rule is called as a junction rule. As the name suggests, junction. What is a junction? Junction is nothing but the processing point or the meeting point of very different wires which are going through different directions. Okay. So junction rule, so at any junction the sum of the currents entering the junction is equal to sum of the currents leaving the junction. Very easy rule. Just to explain to you, I will use first of all my same example. Let us suppose this is that junction, and let us suppose there are 3 wires. Let us say this is one wire, this is one wire, this is one wire. If let us suppose the current which is entering is denoted by capital I1, and let us suppose after this junction in the above and below directions the current which is going is denoted by I2 and I3. Please make sure, please look over here carefully, that the current I1 is moving towards the junction and the current I2 and I3 are moving away from the junction. Therefore, according to the Kirchhoff's first rule, that is junction rule, here I1 is equal to I2 plus I3. So very easy rule. So as the number of junctions increases, you just need to equate the complete currents which are going inside to the number of currents which are going outside. Okay. So this junction, this applies equally well if instead of a junction of several lines we consider a point in a rule. So we are understanding this as a point. The proof of this rule follows from the fact that when currents are steady, there is no accumulation of charges at any junction or at any point of the line. So basically the energy is conserved, energy cannot be sustained at any point, it has to be moving only every time. That is why we can understand this rule, and hence this rule is proved. The proof of this rule follows from the fact that when currents are steady, there is no accumulation of charges. So there is no charge accumulated here, there is no charge accumulated here, and so on, at any junction or at any point in a line. Thus the total current flowing in, which is the rate at which the charges flow into the junction, must be equal to the total current flowing out, and hence I explained you this example which has been shown here. Okay, so let us move on to the next point now. The next point is the loop rule. So first of all let me explain the loop rule, and then I will try to explain what is happening here in this figure. Okay. So second is that loop rule. What is a loop rule? The algebraic sum of the changes in the potential around any closed loop involving resistors and cells in the loop is 0. What does it mean? Let us suppose I am taking this loop as a consider. So if I start from this point, if I keep on taking every potential drop or every potential increase across every point here, then the summation of all when I reach this point again should be equal to 0. This is the complete loop rule. So these are only 2 rules, and using this we can solve many different applications or many different things regarding current electricity. Okay. So the rule is, this rule is also obvious, since the electrical potential is dependent on the location of the point. That means if I go and move to the same point again, then the value at that point again should be 0 only, that point should be same only. So constant minus constant should again be 0, and hence this can be proved. Okay. Thus starting with any point, if we come back to the same point, the total change must be 0, quite evident, which I just spoke, that the potential at that point again should be same. So the potential at that point at the initial time, after after going through a loop, at that point again should be same, and then P minus P should be equal to 0, hence the change should be 0. So in a closed loop we do not come back to the starting point, and hence the rule. So this is the complete thing. So now let us move on to this concept here. So at the junction A, so let us suppose I am going through the junction A. The current leaving is I1 plus I2. As you can see, the current is leaving here I1 and the current is leaving here I2, and the current entering is I3. So current entering is I3 here. The junction rule says I3 is equal to I1 plus I2. Quite evident. So it was the first rule. So if I just make it again here, so what I was trying to explain here, let us suppose this is at junction A. Let these be the 3 wires. The current going inside is, let us say, I3, the current going outside is, let us say, I1 and I2, then by junction rule it is quite evident that I3 is equal to I1 plus I2, that is the total current going inside the junction is equal to the total current going away from the junction. Okay. Now next line is at point H the current entering is I1. So quite evident because there is no other wire, so therefore the current here will be I1 only, the direction will be in this way. There is only one current leaving H, and by junction rule that will also be I1, quite evident. So if we try to go in this portion here, the current which is passing here, that is the total current going inside the junction should be equal to the total current going away from the junction. Hence the current which is going here, this should be the inside and this should be away, hence it will be I1 again, hence the again junction law is validated here. Okay. For the loops A, H, D, C, B, A. So now look carefully as I will try to explain you the loop rule here. So what is A, H, D, C, B, A? A, H, D, C, B, A. So this loop we are talking about, this loop we are talking about. Now see, and A, H, D, E, F, G, A. So this is another loop A, H, where is H? H, then D, E, C, B, A. C, where is C, B, A, H, D, A, H, D, E, F, G, A, E, F, G, A. So that means the complete rule. They are first taking a small loop here, and then they are taking a big loop here like this, and they are trying to just find out some equations so as to we can find out the value of different currents I1, I2, I3 and so on. Okay, so the first loop, so let us move on, let us start from this portion. So I will try to go very slowly now. So let me start from this portion. So first of all, if we go in this way, if the loop is in this way, we are assuming it in clockwise sense, and the current which is in direction of this only, that means every resistor will try to decrease the potential, and every voltage or battery will try to increase the potential, as long as the direction in which we are moving has to be same as the direction of flow from negative to positive for the cell. Whatever I spoke, I will try to explain using the example here. So first look on here, and then I will try to explain if anything matters left. Okay. So let me start from this portion. So if I move to this 30 ohms, then due to this 30 ohms there will be a reduction in the potential. Why? Because the current in the same direction, and every resistor try to decrease the potential. So therefore I will write minus IR. So I is I1 and resistor is this. So let me write like this only, minus I1 into 30. Okay, then H point is reached, nothing is happening till this portion, and then you can see that as this potential is reached, it is from negative to positive direction. That means there is an increase in the voltage. If for example let us suppose there would have been in this direction, then there would be a negative potential, hence it will decrease the potential. But here because it is in this way, hence you will write plus, what was the 45 volts is the potential difference, therefore you will write plus 45. Next is again a resistor of 1 ohms, then we will write minus. Please look over carefully, I3 is the current which is flowing through this, therefore it will be minus I3 into 1, again 40 ohms, that is minus I3 into 40, then going above we are reaching the same point, then hence it will be equal to 0. So just seeing the equation here, that will be nothing but minus 30 I1 minus 41 I3 minus 41 I3 plus 45 is equal to 0. So as you can see, this is the same equation which is written here, minus 30 I1 minus 41 I3 plus 45 is equal to 0. Now let me derive the equation, second equation similarly in this manner. So as you can see, so the second loop is nothing but this complete big loop. So let us move on to this big loop now. So as you can see, if we start from this portion here, so it will be again minus 30 minus IR, so minus I1 into R, then D, and then this 20 ohms will be explained, quite evident. As you can see, I2 is moving in the opposite direction of our loop placement, hence it will be plus I2 into 20. Then again moving, again 1 ohm resistor will again have a positive direction. Why? Because the current is flowing in opposite to the loop, hence it will be plus I2 into 1. Now for the what we can say voltage battery case, we can see that it is going from plus to negative. If it is going from plus to negative, hence it will be minus sign here, therefore it will be minus 80 equal to 0. Therefore just iterating it again, so it will be nothing but minus 30 I1 plus 21 I2 minus 80 is equal to 0, and hence this is the second equation which is written here. As you can see, minus 30I1 plus 21I2 minus 80 equal to 0. Hence, what were the three equations which we got? Just let me write it again here. So, the first equation which we got was I1 plus I2 is equal to I3. Second equation which we got was minus 30I1 minus 41I3 minus 41I3 plus 45 is equal to 0, and the third equation is minus 30I1 plus 21I2 minus 80 is equal to 0. Hence, these are the three equations which we got. As we know, three equations, three unknowns, and we can find out the values of I1, I2 and I3, and that was the complete analysis of, that is the complete application, that is the complete use of Kirchhoff's rules. Okay. So, this is the complete concluding. Let us move on with one of the example. So, if I give you this example and I ask you to solve this using only the concept of series, resistors and parallel, then it will be quite difficult to solve this example. But if we take into consideration Kirchhoff's rules, then this example can be solved very easily. So, let us look over carefully and we will try to explain, I will try to explain this very carefully, very easily to you. So, the example says that a battery of 10 volts and negligible internal resistance. So, internal resistance is negligible, hence we can assume that the value of small r is approximately equal to 0. Okay. So, battery is 10 volts, so battery 10 volt is explained here or installed here, and negligible internal resistance is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors, each of resistance 12 ohms. So, there are 12 edges of a cube and hence there are 12 resistors, and it is connected, 10 volt battery is connected at the opposite end, these diagonal opposite ends. Okay. Now, determine the equivalent resistance of the network and the current along each edge of the cube. Quite evident, we just need to find out the value of R equivalent, and also we need to find out the value of current which is passing through each of the resistors. Okay. Let us move on. So, please look at the solution now. The network is not reducible to a simple series and parallel combination of resistors, basic case of why we are applying this after Kirchhoff's rules. There is, however, a clear symmetry in the problem which can be exploited to obtain the equivalent resistance of the network. So, the paths A dash, so let us suppose this is the path A dash here, AD and AB. These are three symmetrical paths. If you can see, these are three symmetrical paths. Why they are symmetrical paths? First of all, it is passing through this point A, which is the incident force of the battery, and then every of those 3 points have 1 ohm resistor. Hence, till this point we can assume that the current passing through both, all of 3 them will be same. Okay. So, where was I? So, the path A dash, AD and AB are obviously symmetrical placed in the network. So, let us assume for now that the current passing through these 3 resistors should be I. Next, so thus the current in each must be same, which is I. Now, further at the corners A dash, B dash, A dash, B and D. So, this is A dash, this is B and this is D. The incoming current I must split equally into the two outgoing branches. Why it must split equally? First of all, because it has to be because the resistors after those are same, and why? Again the junction rule has to be applied, that is the current totally going in should be equal to total current passing out, hence it will be same again. So, using these two different rules we can find out that at this B point I by 2 and I by 2 are going in this direction, and in these two points these are going in this direction, and in this portion okay, and in this portion this is going in this direction. Hence, we know for now the currents in which let me just use different color. So, we know in this sense, let me change another, wait. So, we know in this, 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 we know in this. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, we know in 3, we just need to know what are in these. Okay. So, let us move on what is in the next line here. So, in this manner the current in all the 12 edges of the cube are easily written down in terms of I using Kirchhoff's rule and symmetry in the problem. So, now after this point we need to know the value at these portions. So, again we can apply the junction rule here. So, it will be I by 2 plus I by 2 will give you I here, similarly I by 2 plus I by 2 will give you I here, and similarly I by 2 plus I by 2 will give you I here. Hence, finally we know the currents in each of these resistors. Now you need to apply the loop rule. I will apply the loop rule in the next part. Let me stop it here only. So the concluding part of this lecture was that I explained you the two rules of Kirchhoff, and then finally I explained you how using these rules we can find out we can divide the currents in different resistors if it is a complex resistor. So let me stop it here. In the next lecture I will continue with this example only. So thank you.